You've seen them, right? Those massive storage tanks on the side of the highway or at an industrial plant. We're surrounded by these silent giants. But what happens when you add one simple thing? Heat. Well, that's when they can fail with catastrophic force. Today, we're going to break down the fundamental physics of why.
So what is it? What's the catalyst that can turn this piece of incredibly stable engineering into a ticking time bomb? Believe it or not, the answer is one of the most basic forces in the universe. All right, to get why this is so dangerous, first we have to understand what's going on when everything is, well, normal. Let's take a look inside one of these giants when it's just sitting there, completely stable. So inside any sealed-up tank, you've got a set amount of gas in a set amount of space. It's a totally closed system, and it's all held in this perfect balance. The pressure is known, it's controlled. This is our starting point. Everything is stable, everything is safe.
But see, that balance is incredibly fragile, and it can be completely shattered by one of the most fundamental forces there is: heat. The second heat gets involved, the rules of the game change completely.
And this is the key to everything. The ideal gas law. It's a cornerstone of physics, and it basically tells us that pressure, volume, and temperature are all locked together. They have this really precise mathematical relationship. For what we're talking about, you just need to focus on two letters: P for pressure and T for temperature. And here's the absolute bottom line. The tank itself can't get bigger, right? Its volume is fixed, so that V in the equation is constant. That means if you crank up the temperature, the pressure has to go up to keep the equation balanced. It's a direct one-to-one relationship, and it is unforgiving. More heat equals more pressure, period. Okay, but that simple ideal gas law is just that. It's for an ideal situation. In the real world, especially under the insane conditions of something like a fire, the physics gets way more complicated. And honestly, way more dangerous. So, an ideal gas is like a perfect student. It follows the rules exactly. But the kinds of industrial gases in these huge tanks, they're not ideal, especially not when you put them under intense heat. They become what we call real gases. And their behavior, well, it can get unpredictable in some really dangerous ways. And that's where scientists bring in the real gas law. See that letter Z? That's the compressibility factor. You can just think of it as a reality check. It's a little variable that accounts for how gas molecules actually start bumping into each other and taking up space when they're getting squeezed by all that heat and pressure. It's how we figure out what really happens in a worst-case scenario. So, let's talk about that worst-case scenario. Let's put this physics into action at a facility fire. This is the moment where all that theory becomes a terrifying reality, and it happens fast.
Okay, boom. A fire breaks out. Our perfectly stable pressure tank is suddenly right in the middle of the flames. The clock has just started ticking. The outside of that steel tank just starts absorbing a crazy amount of energy. We're not talking about the temperature just rising a little bit. It is skyrocketing.
And that heat, it rips right through the steel walls. The gas molecules inside start soaking it all up. They start vibrating, moving faster and faster, and crashing against the inside of the tank with more and more force. And remember our formula, right? More heat, more pressure. This isn't some gentle little rise. It's a violent, uncontrollable spike. The pressure inside is now screaming past every safe operating limit. It's literally hammering against the walls of the tank with a force that's just unimaginable. It's getting closer and closer to the absolute limit the steel can handle before it just gives way. Now I know what you're thinking. This sounds like a total disaster just waiting to happen. But it's not. And the reason is, engineers know this physics. They expect this exact scenario, and they build the solution right into the tank itself. And this is the absolute core idea behind pressure vessel safety. Engineers know this thermodynamic reality is a threat, and that's exactly why they design every single vessel with something called a maximum allowable working pressure. You'll hear it called MAWP for short. So what is MAP? Well, it's not the pressure for a normal day at the office. No, this is the absolute red line. It's the highest possible pressure the vessel's steel and construction are built to handle before there's even a chance of it breaking. It's the safety limit, and it's set way, way above normal. And this visualizes it perfectly. Look, way down here, that's your normal, everyday operating pressure. But way up here, that's the MAWP. That huge gap between the two, that's your safety margin. That is the buffer zone engineered into the system specifically to handle these crazy, unexpected spikes, just like from a fire.
And that really is the whole story in a nutshell. The laws of physics create this very real, very serious risk. But a deep understanding of those exact same laws is what allows engineering to come up with such an elegant, life-saving solution.
It really makes you stop and think, doesn't it? I mean, this is just one example. What other invisible forces, what other incredible pressures are being carefully and safely managed in the world all around us, every single day, and we don't even have a clue?